Hello, this lecture will cover pages 129 through 134 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 8C, Review of Complex Numbers. I think you've all seen complex numbers in previous math classes, but now we're going to put it to application or use in an analysis of sinusoidal circuits here in this circuit analysis class. On page 129, let's do a real quick review of the complex plane. If you remember, there was an equation referred to as Euler's equation, and this was Euler's equation. Now, if you haven't seen this in math before, don't worry about it. It says e to the plus j phi, where j is an imaginary number. It's equal to the cosine of phi plus j sine of phi. This is referred to as the complex exponential form over here. And this is referred to as a complex sinusoidal form. Now, if you take a look, I've just rewritten this equation down here. And this is a complex plane where this is an imaginary axis, j, and this is the negative imaginary axis down here, minus j. This is a real axis, and this is the negative real axis. What we're going to do is we're going to put a radius vector on this that has a length of 1, of unity here. And we're just going to rotate it around this complex plane here. And we're going to project points at this point, and this point, and this point, the whole way around the circumference of this circle. And you could see whenever this radius vector is out here, it has in the horizontal axis with the angle of 0, has a radius of 1, and it's a completely real component. As it goes through these 90 degrees right here, it's going to have a component that's not only real, but a component that gets less real and more imaginary to this point. And then we just continue around through these different quadrants here. You can express this point right here as some magnitude e of plus j phi, where that coefficient on e is a 1 because this radius vector here is a 1. Or you can express it as a real part, which is a cosine of phi, which is this adjacent side. If you draw this triangle to that point, it's the adjacent side plus the opposite side from this point. You've had that in trig before. You could express this point either in terms of the complex exponential form or the complex sinusoidal form. In electrical engineering, we replace the I-axis with the j. So a lot of textbooks, you'll see this as I, and you'll see this as negative I. Well, we don't use I as the complex variable, as the imaginary number, square root of minus 1, because I is current in electrical engineering. So you'll always see j as the imaginary component, where j is equal to the square root of minus 1, imaginary number. Representing any point in a complex plane can be done in two forms. It can either be done in rectangular form, where it has a real part, plus or minus an j imaginary part, or in polar form, where it has that vector, which is no longer going to be a unity 1 vector. It's going to be some value, c, at an angle of phi from this 0 degree point, measured counterclockwise. So you've seen rectangular form before, and you've seen polar form. This is the only form that we're going to use for rectangular. It's the real part plus or minus j, the imaginary part, where j comes first and the coefficient comes second. The polar form will have this magnitude at some angle. Now, if you take a look here at the complex plane, what I've done is I have the real part here, plus real. I have imaginary real. I have the plus imaginary, and I have minus imaginary. This is referred to as the first quadrant. This is the second quadrant. This is the third quadrant, and this is the fourth quadrant. You already had that in trig. And we could pick a point out here. Let's pick a point right here. And that point can be represented two ways. It could be represented as a real component, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and a plus 1, 2, 3, 4, 5, 6, 7. So that point is 7, comma 7. Well, the way we'd represent that in rectangular form isn't 7, comma 7. They're both shown as real numbers. We'd show that as a 7 plus j7. So that point in rectangular form is 7 plus j7. Or we can have a vector coming out here like this, and we can represent it as a magnitude here, c, at some angle phi. And you can just use your trig to come up with the value of c and come up with the value of phi, your trig relationships, if you know that this real distance here and here is 7, and this real distance is 7, and this imaginary distance is also 7. What about we take a point down here? We could represent this point as a real 1, 2, 3, 4, 5 minus j 1, 2, 3, 4, 5, 6. That's one way of representing that in rectangular form. This point on this complex plane. Or we can draw a radius vector to that, and we can represent it as some c, this length here, using the Pythagorean theorem, at some angle phi, which will be a negative angle. And we could pick any point over here in the second quadrant, or any point over here in the third quadrant. We can do the same thing. Represent it either rectangular form or imaginary form. Let's take a look on page 130, how you convert between rectangular and polar. Well, here's a general rectangular form, and we need to get this into a polar form. Well, once you know the rectangular form, using the Pythagorean theorem, this magnitude on the polar form is simply a squared plus b squared, the square root of that. And the angle associated with that is always the inverse tangent of the imaginary part over the real part. The imaginary part over the real part. These are the two conversions. The angle phi here is always measured counterclockwise from the positive real axis. It's always measured from this point right here. Either referenced this way or referenced this way. We have examples to show you that. So I want you to convert the following rectangular to polar forms here. I want you to take your time, and I want you to convert that, convert this, and convert that. Stop the video and try it and see what you come up with. And see if you got these answers. First of all, 3 plus j4. You should have got 5 at an angle of 53.13 degrees. Well, let me tell you where most people mess up here. You basically have to take the 3 squared, add it to the 4 squared, add them together, square root, and you get your 5. But this angle messes people up. I want you always to take the imaginary part over the real part. In this case, 4 divided by 3. Get a value and hit inverse tangent on your calculator. You're going to get 53.13 degrees, but you have to put that in the correct quadrant. You have to either put that in quadrant 1, 2, 3, or 4. 1, 2, 3, or 4. So take a look. You're going to get the 53.13 degrees, but if you have a positive real and a positive imaginary, it's going to put it in the first quadrant. So the angle's just the 53.13 degrees. There's your answer. What about this one down here? Same thing. That's going to be an angle in the first quadrant. So when you get your 36.87 degrees, you know it's a positive real, positive imaginary. Positive real, positive imaginary. It puts it in the first quadrant. They're pretty easy. What about this one down here? You just take the 5 and divide it by 10. You can't take a negative 5 and divide it by 10. Or you can't take the 5 and divide it by negative 10. You don't know where that negative sign gets distributed. Does that negative sign get distributed on the 5 or the 10 when you divide 5 divided by 10 and take the inverse tangent of it? So how do you get around that? Forget about the sign here. Just take 5, divide it by 10, inverse tangent. You're going to get 26.57 degrees. And you have to put that 26.57 degrees now in the correct quadrant. That's where the signs come in. If you have a plus real and a negative imaginary, a plus real and a negative imaginary, that puts it in the fourth quadrant. So that angle in the fourth quadrant would be a negative 26.57 degrees. That puts it in the fourth quadrant and you're done. What about down here? What about this problem right here? A negative 140 minus J60. Well, you can take the 140 and square it and add it to the 60 square and take the square root, you get your 152.32, no problem. But it's a 23.2 degree angle if you take 60 divided by 140 inverse tangent. But that's not the answer. You could say it's an angle of 23.2 in the third quadrant, but you don't want to qualify it that way. You have to place that angle in the correct quadrant. Well, if you have a minus real and a minus real and a minus imaginary, a minus real and a negative imaginary, it puts it in the third quadrant. So that's an angle in the third quadrant here. That angle is right here. That angle is the 23.2 degrees. Placing it in this quadrant, you have to take this 180 degrees and add it to that 23.2. Therefore, the answer in this problem is 203.2 degrees. So I want you to go ahead and try these. I want you to try each one of these. Just figure out the angle and then put it in the first, second, or third, or fourth quadrant and see if you come up with the answers. Stop the video and try it. And if you did it right, this is what you should get. There's the answers to that problem. Continuing on, what about on page 131? What about conversion from polar to rectangular? Well, in this case, you're going to have a magnitude at some angle, and you want to get it in terms of the rectangular form, a real part plus an imaginary part. Well, A, the real part, is simply equal to C times the cosine of phi. That's trig. And B, the imaginary part, is equal to C times the sine of phi. So convert the following from polar form to rectangular form. I want you to take your time and do each one of these and see if you can use the relationship I'm showing you here to get the real part first. 30 degrees, take the cosine of it times C. That gives you the real part. Then take 30 degrees, take the sine of it times C, in this case 10. It gives you the plus or minus J, the imaginary part. If you did that correctly, here's the answers. You end up with those answers right there. Make sure you can go from rectangular to polar and from polar to rectangular. Now, as a review here, what you should be able to do is go back and go from the polar to the rectangular on not only those problems, but on these problems as well. Make sure you can go from rectangular to polar and polar to rectangular. You're going to be doing that a lot next number of weeks. Page 132. When you're working with these complex numbers, whenever you need to add or subtract complex numbers, it's more easily done in rectangular form, not polar form. So keep in mind, if you ever want to add and subtract complex numbers, put them into rectangular form. It's a lot easier to perform the math. Let me show you what I mean. If you look at these two examples here that I have on this page, it's sort of hard to see, so I'm going to put it in a different form right here. Let me see if I can find the first example here. What I have is this. I have a source voltage, V of S, and it's a complex number with magnitude and direction. And I'm going to show it V of S like this. It's not a DC source, it's a sinusoid. I don't know what this element is here. I don't know what this element is. This element is a combination of R, L, and C, resistors, inductors, and capacitors, or RC, or just R, just any single element. We don't know what's inside these boxes. I know the voltage across this element is 3 plus J4, and I know the voltage across this is 8 minus J10. That's the voltage across each one of these. I want to find the voltage at the source with respect to time. not the polar form out here, not the complex form. I want to find the voltage with respect to time. So how do I do that? Well, I know through Kirchhoff's voltage law that the rise has to equal the drops. So Vs out here has to be equal to the sum of these two. 11 minus J6. I didn't show you all the math. I'm keeping these in rectangular form, and I'm simply just adding them up. Now, in order to get back to the time domain, I have to get that in. Remember, we have to get this in this polar phasor form. So I convert this rectangular to polar. I get 12.53 at an angle of minus 28.6 degrees. That's in volts. And now that's the maximum value. These phasors are always represented as cosine. That's what we're going to use as a standard. I'll be talking about that a lot in a minute. But for now, when you go from the rectangular form, from the polar form or the phasor form back to the time form, we're always going to assume that this phasor form here is a cosine representative of the value. So there's your maximum value, 12.53. Cosine, these are always going to be in the cosine form. I just told you that. We don't know the frequency, the angular velocity. It's just omega t, and the phase angle is a minus 28.6 degrees. There's your answer. Look at that problem, and I want you to find V of S with respect to t out here. What's the forcing function on this circuit? And here it is in the time domain. Let's look at the next example here. In this second example, I give you two currents, and I'm going to find the total current. Well, here's the problem. Made it more realistic. I have a parallel circuit here, and I have a total current coming into this node, and it branches I1 and I2. I want you to find the time equation for this total current here. If I1 is equal to this phasor form and I2 is this phasor form. Well, you can't add these polar forms up. If you're going to add or subtract, they have to be in rectangular form. That's what this is all about. Since we need to add I1 and I2 to get IT, that's Kirchhoff's current law at this node up here, we have to convert I1 from this polar form to the rectangular form, and there it is. And we have to convert I2 from this polar form to this rectangular form, and there it is. Now I simply have to add these up, and when I add them up, I get this rectangular form. Since we're adding, we want to keep them in we want to put them in rectangular form. So far we're at this point right here. Now in order to go to the time domain, we have to get this rectangular form back to the polar, because that's where we can pull, remember, the maximum value of the waveform, and that's where we can pull out the phase angle. And that's a cosine representation. Remember we said that. So it's 26.93 maximum value times the cosine of omega t plus the phase angle. It's a plus phase angle, plus 111.8 degrees. In review, always use rectangular form to add or subtract complex numbers. So you have to use this conversion, which you can see on page number 131. Now we're going to take a look at multiplication and division of complex numbers. They're more easily done in polar form, not rectangular form. So here's another example that I have. And I've worked this example out on another sheet of paper here for you. And this is it. I have a simple series circuit. I have the forcing function V of S in polar form here. And I don't know what Z is in this case. I don't know what Z is, but I'm going to give you the current. And I'm going to give you the voltage. I want you to find the impedance, which is the AC resistance, if you will. What's inside that block? If V of S, the source voltage, is 10 plus J20, and the total current is 5 plus J30. I think that's the problem we're working here on this. Let me take a quick look to make sure. Yeah, that's the problem we're working. It's just Ohm's law. The impedance is equal to the voltage over the current. Well, there's the voltage in rectangular form. There's the current. You could multiply both the top and the bottom by the complex conjugate of the bottom. Remember we used to do that? It's called rationalizing this. You can multiply the top and the bottom by the complex conjugate of the denominator here, which is 5 minus J30. So when you do that, what you'll do is you'll be able to get rid of this imaginary number in the denominator, and you can complete the problem. But you still have to get the polar notation sooner or later. What I recommend is going straight from here to here. I don't recommend rationalizing. Remember, if you're going to multiply or divide, in this case, impedance is voltage over current, I want to go ahead and divide. So I convert the 10 plus J20 into its polar form. I convert the current 5 plus J30 into its polar form. I make the division and I get the impedance is 0.735 at an angle of minus 17.11 degrees, and that's in ohms. But in that form, the impedance doesn't do us any good. We have to go back to rectangular form, because what we can do in rectangular form, and this is extremely important, is we can pull out the real part, which is the resistor that's in this box, and we can pull out the imaginary part, which is not imaginary at all. In this case, it's a capacitor that has a reactance, a capacitive reactance of 0.22 ohms. Let me talk more about this in the next video. But for now, I just want you to notice that you have to take this polar form to a rectangular form, and it's in the form R. It's a real part. It's still real, but resistance is what we're looking at here. This real part here is going to be resistance. This imaginary part here is going to be inductive reactance, and this imaginary part here is going to be capacitive reactance. We talked about this before, where this really is the minus JX sub L axis, and this is the plus JX sub L axis, which is inductive. We said anything in this first quadrant is inductive, and this will be your minus X sub C, JX sub C, capacitive reactance down here. Anything in this fourth quadrant here we said was capacitive reactance. So we're going toward that goal right now. So here you can take a look at this, that R is equal to 0.7 ohms and the capacitive reactance is 0.22 ohms. I know it's capacitive reactance rather than inductive reactance because it's negative. It's negative here, which puts this in the fourth quadrant if you look at it. This is in the fourth quadrant, this is in the fourth quadrant, either one. Polar form, rectangular form. So our impedance diagram simply looks like this. There's our impedance diagram, where the real component's 0.7 ohms and the imaginary component's 0.3 ohms. And then finally, I have another example here. This example here is more easily seen here. If I can find it. There it is. Keep in mind here, always use polar form to multiply or divide complex numbers, and you have to see page 130 for that. So here's this one example that's on the next page. I clear it up a little bit. I have current I, in this case right here, and I have the voltage V across that element. I have the current through that element, and I have the voltage across it. I want you to find that impedance. So here's what V of T is equal to. Here's what V of I is equal to. I want you to calculate Z from these two quantities and then show the impedance diagram. Don't forget, the first thing you have to do is convert these to the phasor form, to the polar form. These are in the time domain. So you have to convert these from the time domain to the polar form. Both of these, and you can start your calculations. I think I worked this out on the next. Well, here's my solution to it. Here's my solution to it. There's V, there's I. Now I can do my math and I can see that's purely real. Here's the impedance diagram. There's no reactive component, either inductive reactive or capacitive reactive. It's all real. It's along this axis. It's 6 plus J0. You just show that as 6. So here's two more problems I want you to look at on your own. What if V of T is equal to this and I of T is equal to this? I want you to find Z, the impedance, and do a impedance diagram. And then what if V of T is equal to this in the time domain and I of T is equal to this in the time domain? I want you to find Z. and then do an impedance diagram. And remember, when you find Z here, it may have a real plus or minus a reactive component. This down here is going to have a real plus or minus a reactive component. Now you don't know if it's X sub L or you don't know if it's X sub C. You don't know which one of that is until you work this problem out. If it turns out to be in the first quadrant, it's inductive reactance. If it turns out to be in this quadrant, the fourth quadrant, it's capacitive reactance. And that concludes this lecture.